With this video, we are going to present our end of studies project about the conversion of a depth map image to sound representation. The goal is to try to improve the living conditions of blind people by helping them to identify the obstacles they encounter while walking in order to better avoid them. In order to do that, we will use a depth map image. As you can see, it is a representation of the depth of the real image, which represents the distance of the object from the camera. We will then perform image processing on it. This project is therefore composed of several components. A computer. An audio headset so that our user can hear 3D audio representing the information obtained from the depth image. And a casing created using a 3D printer which assembles a RGBD camera and the printed circuit board of a mouse. The device looks like this. So how does it works? The device does not emit the sound continuously. To obtain it and have the information of the image, you would have to press the button of the object. After that, we have the capture of the image and the corresponding sound emitted. The audio represents the image's information from left to right. To process the image, we resize it in order to be able to apply the mask full of circles and simplify the colors. Next, we select the color of the circle with the lightest color in each column. As a reminder, the lighter the shade of gray, the closer an object is. However, the audio that can be obtained with this sequence of colors still contains too much information, which can be complicated to interpret. For that, we will limit our audio to a series of 5 sounds. So, we then divide our line into 5 and once again we take the color of the lightest circle. Now we need to categorize these 5 colors. To do this, we associate our colors with one of these categories. Very far, far, near, very near. To know which category our color falls into, we associate a color interval with each category. Our audio will be the following sequence of sounds: far, far, near, 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 near. It will sound like this. We can see with a Fourier transform that the transmitted frequencies correspond to those defined by our expected categories, frequencies at 400 Hz and 600 Hz. To test our device, we created this configuration. The user does not move and simply rotates from 0 degrees to 180 degrees. Every 20 degrees, the user captures the image and say if there is an obstacle or not in front of him. That defines the prediction of an object in our confusion matrix. This means that for a true positive there is an obstacle and it is detected by the user. For a false positive, there is no obstacle but the user predicts an obstacle. For a false negative, there is an obstacle but the user predicts no obstacle. For a true negative, there is no obstacle and the user predicts no obstacle. Here we have more true positive and true negative, so our device is working. We also tested our device with someone that did not work on our project. He has to go to the final point without touching anything. As we can see, the user succeeded. Although your device is operational, there are still limitations. In fact, you have to press a button to start the scan, so you don't have real-time information. The camera range does not capture correctly if the object is too far or too close, as the depth image is not clear. We also only process the middle part of the image, so we need to take multiple captures to vertically reconstruct the path in front of us. There is also white crackling which can distort our image processing. And the device is connected to a computer which does not make it easy to transport. Despite our limitations, the device proves its effectiveness. Indeed, the objective is fulfilled. Thank you for your attention.